Dobré odpoledne. Vítejte. Jsem rád, že ještě stále některé z vás pořád můžu přivítat na přednášce. Nemá někdo nějakou otázku, myšlenku, přání? Vtip. Aktualitu. Mám tady rajčata, můžu nabízet za otázky. Oh, and I should speak in English. Yeah. I was just giving a lecture in Czech, so if you are watching the recording, welcome. Also in English, and we can start. So we introduced the possibility of start using the models in our reinforcement learning settings. So instead of having a tabular way, like really just a list of numbers of the estimates of the returns, we will have a model which will be used to model either the value function or the action value function. In all cases, the average behavior of our agent using some parameters. And we decided to minimize this by using a weighted version of the mean square error. Now the weighted version might sounds weird, but we actually write it there so that the natural way of simulating the episodes and then just taking the result as the training data works. Right? Because if we generate data in this version, like by really interacting with the environment, we get not uniform states and actions, but we get states and actions which are visited by the agent. And we have called this to be the on-policy distribution. Right? So we said, okay, this distribution over the states tells us exactly how often the various states are visited. And so when minimizing this mean square error, the resulting update was actually very similar to what we did previously, right? So if you look at what the SGD update looks like, then there is the learning rate there, and then there is the gradient of this part. So the derivative of the square of something is the something, right? So here is the difference between the real value function and our approximation, and then there was the derivative of our model. In case of a one-hot representation of a linear model, this was just a vector which set a lot of zeros and then 1, 1 on this one weight, which corresponds to the given state. So this really was exactly the update which we have derived previously, but with a different motivation or origin. And again, we could have used the Monte Carlo or the temporal difference methods, and they differ only in how they estimate this value function. Like this is the true unknown value function. We can just generate estimates of that, and we can do it by either simulating the whole episode, as in Monte Carlo, or simulate just a part of the episode using n-step temporal bootstrap, and then estimating the remaining part of the episode by looking at the value function which we have. So the algorithm for doing the TD update is, well, exactly the same as before, or as you would expect, as it was on the previous slide, but it's called semi-gradient. So the question is, why is this called semi-gradient? And the reason for that is that when you look at this formula, then we have the prediction of our model here, but we do not really backpropagate through that, right? We don't consider how changing this would influence the final outcome. So why is this so important? Is that normally for SGD, we know that it converges. Right? If our update looks like that we take the original weights and say weights minus alpha times the gradient of some error function, then this kind of update will converge under some conditions to a local optimum. But when we look at this, I said that we have derived it using the gradient of the error, but when we did it, this thing, like real value function didn't depend on any parameters. If it did, then the derivative of that would also have to be present. And then only later we said, and yeah, so this thing, we will actually approximate it with our model. And so this has the consequence of this update not to actually be any gradient of any function. Right, so this specific formula, which I have there, is not derivative of anything. That means we actually don't know if this will converge somewhere or not. Well, that's not so, and even for the case where we wouldn't change the policy, right? We knew that like doing the value estimation would converge if we would use Monte Carlo. Like if you keep a fixed policy, right, then just evaluating the policy by doing a lot of updates does converge. It's just a value iteration or policy iteration, depending on how we look at it. But here we wouldn't have any guarantee that it would actually work. So first thing is, why is this not a gradient of anything? So why is it is that we actually had some parameters hidden here. So when we were computing this derivative, if this, we would also need to include the derivative of that part, and we didn't do it. But of course, this is just me waving hands around. So to do it correctly, or at least sketch it correctly, then let's consider one very simple model. So just a linear model, right? So in the linear model, we have weight for every feature representation of the state. And we will assume that there is some function j such that this is its derivative. Right? So that's what I have written here. Okay. So when we compute the derivative with respect to wi, right, then it would be this part. And then here we would have the derivative of this with respect to wi. And as we have implemented it, it would just be the ith feature of the state which we have. This is one specific function because it will be enough to show that it doesn't work, even for this function. So now how we can show that such a j doesn't exist? Well, if it existed, then the second derivatives would need to be symmetric in a sense that if we computed the derivative with respect to wj and then wi, or in the other order, wi and wj, they would need to be the same. Like if a function exists and it has second derivatives, then this needs to hold. And we will show that it does not hold, so we couldn't have started from a simple or single loss function. So this is just really a lot of technical details. So let's have a look at it. We'll start with this part, right? And now, so that's this one, right? And now let's compute the derivative of this formula with respect to wj. So what happens, RT goes away. From this part, I will keep just the feature j, right? Because we assume for simplicity that this is just a linear sum. We are computing the derivative with respect to wj, so only one of these terms is the interesting one, and that's the jth feature, right? And then the same thing here, so again, the jth feature here. And here we just copy what was there because, well, no more computing of derivatives in that place. And now if we have swapped, I should do it in another color. If we have swapped these two things, then what would have happened? Well, this j would result in j here, and this I would result in I here and here. And now when we look at it, then there is one term which is common for both of these. So that's the ith and the jth feature of the current state multiplied. But this part is not symmetrical. So you can easily come up with state representations where these quantities would be different. Right? Because here we have st plus 1i, and here we have got sti, and that can change because it's a different state. So even if this is like mathematically boring, it means that we cannot prove that even just the computation of the value function, just doing policy evaluation is not guaranteed to converge with this formula. Yes, a question?
But would it work if there was only a single state?
Yeah, so the question is, if there was only a single state, if it would work.
Because st plus 1 would have to be st.
So if we had a single state, then this argument wouldn't hold. So there could have existed a function whose derivative would be this part in this one specific case. But one of the problems with this proof is that we assumed a very, very simple function. So what we don't know is if this is true, if these things hold, whether there exists such a loss function in all the cases. So my guess is that it shouldn't work also for one state, but then probably the proof would have to go a different way. Because it's still true that if we have started and there would be the approximation or our approximation in st plus 1 w, which is what we use here, then we didn't include it here, right? Because here we should have had this plus the derivative of that, of the st plus 1. I'm sorry, it's not very readable, but we are missing this term there, and I don't think that having a single state would be problematic. It just makes this proof not to work. In any case, this proof is taken from the original paper who did it, because I had no idea how to formally show that there is no derivative. Like, one sees that if you would start with this and do a gradient method and really put the estimate there, if we really use the bound bootstrapping estimate there directly, we would see that we would get something different, but it's difficult to say that there are no other functions. Well, I think that if the function has second derivatives, then this has to be the case. Like, the Hessian matrix always needs to be symmetrical. Yeah, definitely continuous functions, all nicely differentiable until order 2. I don't play nice with other weird functions, so I don't know. But so here the idea is that the function is nice. It's like differentiable until, like, I don't know, at least third order, or if it has continuous second derivatives, then I am kind of sure that the Hessian should be symmetrical.
If they are continuous, then it also. So we have only proven that is known as continuous.
Yeah, we have only proved that in this specific case. On the other hand, all the output loss functions which we use tend to have this property. Like, it's on the output layer, so I'm not saying it doesn't exist, but I assume one could extend it to the case where it's just like, I don't know, Počástek's derivative, or like a finite number of exceptions wouldn't probably, could be handled somehow, right? I would expect. But I'm not that good at calculus, so maybe you can prove me wrong.
But we wanted to prove it so so we know that that it is not easy to prove that this does converge, but for which we only needed the existence, not that the function that exists.
But if we also wanted to use it in practice, we would also need the function. Like if we wanted to, oh yeah, I know, I see what you mean. Yes, you are true, you are right. If we just knew that it existed, we wouldn't, well, still, mostly when you implement it, you really implement it by using the loss function and then letting the framework to compute the derivative of that. So the natural implementation would also require the original function, but of course, we could have done it somehow so that we wouldn't use the implementation and then just use directly this update, even if it's not so straightforward to do it in PyTorch or something. But we could definitely. So yes, you are right. In a sense that we wouldn't need to know it. But right now, the only thing we know is that if it exists, then it cannot have, what, continuous second derivatives or something like that. Thanks. Unfortunately, like in the reinforcement learning area, people don't care much about these, what they consider to be like weird cases, which for many people is the area of their study. So I don't really know of any results in this area where people would have like more rigorous proof. So it might seem to you that I'm just waving my hands around, and that's definitely the case how it's going. But unfortunately, I know of no materials in the world which would actually cover these cases. And I like jumped into the same wagon as everybody else, which says, let's look at how this actually works in some specific situations, instead of like thinking what would happen on the boundary conditions. Because even for the usual Monte Carlo like control, like when you want to come up to the optimum policy, we don't know even for the original Monte Carlo whether it converges. Like we only know that it converges if the policy is fixed. But if the policy changes, then we just hope with this generalized policy iteration, it will converge. And then when it converges, we know that it is optimal. But we even don't know it there. So from this point of view, I agree that this is not rigorous, but it's just in the lines of what people think, why this is not converging. But I don't want to say that it doesn't converge. I just wanted to say that we don't know it yet. But for this specific case, people actually have proven that it converges, but it actually converges to something different than the Monte Carlo solution. So it converges not to the real value function, but if we do this, then we get some value function, which is not the actual one. So from this point of view, either there exists very weird loss function in this specific case, or it converges for different reasons than the one used in the proof of the SGD, but unfortunately to a different optimum, which is kind of complicated. So it converges to some other fixed point, which is usually denoted as WTD. Well, I will just show it on this and other slides, and we won't talk about it much again. But what is known is that the loss, the mean squared value error loss, is somehow limited by the real optimum, but by the factor of 1/1 minus gamma, which is not that great, because if gamma is, I don't know, 0.99, then this is 100. And we know that this is, well, at most 100 times bad as the real solution, which, well, gives us little comfort, probably. I'm not saying that it has this, it's just that this is only the only bound which is known in this specific case. And this only, like this convergence works for the linear case, So when the approximation is really just a linear function. I don't know if something is known in some other cases. In this linear case, this gradient boils down to something very specific. So then you can use a lot of linear algebra tricks to show that we are iterating some matrix which will converge because it has got, I don't know, diagonal, it has got eigenvalues smaller than 1, so repeating it many times will actually give us convergence. But once this function could be verse, we would probably know, we wouldn't know anything. So there is like a visual confirmation or of what this actually comes up with. So if you remember, this is the example which we had on the previous lecture. We had these states from 1 to 1000, and from each state the transition leads to the 100 neighboring states to the left and to the right, and we get -1 when we get to this state, and we get +1 when we get here, and the true value is the red one. And we had Monte Carlo, which like did something like this, right, which kind of worked. It's just that at the end, because it used this weighted version and the probabilities of the states looked something like this, then it didn't really go through the middle, if you remember, but it was slightly higher because the probabilities of these elements was larger, but then it was understandable what's happening. But here, the semi-gradient update will converge to this blue thing, which is, well, completely off for all these values in this bucket. But that's the best what these methods do. But you can see that the semi-gradient is really problematic also from the point of where it converges to. So that this kind of believed people into like not trying functional approximation too much with the temporal difference methods because, well, it's difficult to actually prove anything about it. So it will be much more surprising when we actually come up with a working algorithm in a few minutes or tens of minutes, which actually did something on some real data. Anyway, apart from this small problem of the algorithm converging badly, the algorithms like SARSA or Q-learning can be implemented kind of straightforwardly. Right, during the update, we will just perform this formula, which we don't know which losses it is minimizing, but in any case, we can compute it. And we can do this for the n-step returns and so on. And we can actually solve things like the mountain car kind of situation, right, where we now can consider not just discrete states, but really continuous values on the input, right? That's one of the things which we get by having functional approximation, that we no longer need to use the tiles or something. We can really just take two real numbers, the position and the velocity, and then do the training. Now there is a visualization of how the value function looks like during training. Okay, and this is actually showing with tile encoding, so that's boring. But even for the real case, it would probably look very similarly. And just to see what the training dynamics look like at the beginning, right? We are like exploring things, and because we get -1 reward for every timestamp, we are just saying, well, in all the visited states and actions, we are saying, well, this doesn't work. So the model tries to do something else, and the states which are like higher on the hill are not visited yet, so their value estimate is 0, right? Because we have started with the optimistic initialization. Everywhere we said, yeah, we will end immediately, and that will be great. Then this means that the algorithm is trying to like reach these parts whenever it can. So after some number of steps before it had even finished one episode, the values would look like this. Now these estimates have a like minus sign like swapped, right? So when the value function is -4, it's drawn as 4 here because that's the better way how to look at it. So you can look at it as what is the average number of steps which the algorithm thinks will take to finish from the given state and action. And the reason why is this such a weird hill is that, well, these are positions and these are velocities. So when you are like doing these swings, then when you are at the bottom, you are probably very fast because, well, you have gone downhill right now. On the other hand, when you are on top, your speed is very low, so that's why this weird circular thing is there. And the middle, no, because the middle is that you are down without moving, which you don't do that much. Right? And then, after more and more updates, you'll actually start getting to the output goal, and you will start generating this like trajectory, something like that, which will in the end allow you to like get to the top as quickly as possible. So this was just to have a break, and let's deal with one more problem. Not only that our temporal methods are not sure to converge, we will actually show that there will be situations where off-policy training will actually cause divergence, right? So even if we are doing everything correctly, our model will never train. And for this to happen, there will be 3 important components. One is using off-policy training. The other is to use function approximation. And the third one is to use temporal difference. So to use bootstrapping, so to estimate the returns from our model. And if all these 3 components are there, then we will see that there are cases where even the value or the like policy evaluation will fail. It will diverge, it will not converge to the correct values. So this was meant to be a bad result, and people were discouraged to try functions in these settings. It's actually called the deadly triad in the book, right? So it's like a combination which, if you meet, you will not really succeed that much. So I will show you first on a simple example what the problem is, right? So imagine that we have a state which goes into another state, and that our value function estimate is W for this state, and then it's 2W for this one, right? So this depends on how we represent, like what the features looks like for the given state. But you could imagine that this state has some representation which multiplies this weight by 1, and this state has some representation which multiplies it by 2. Like there are many ways how you can achieve that. And now you can imagine what will happen if the training commences. So let's say that initially this W will be 10. So the temporal difference error, like, how does it look like? Well, if we get a reward of +0, then what we observe after this one step is like 0 plus gamma times the value estimate in this other state. So that will be like roughly 20. And what the value estimate looks like in our state, well, that's roughly 10, right? But the TD want these 2 things to be similar, right? So the TD error is the difference between those. That's the estimated return minus the current value. So the error will be large, it will be 10, and it will say, okay, so this needs to be increased, right? Because we know that if we will do one step and look there, it will say 20, and we only say 10, so we need to increase it. And you can see the flaw in the plan, right? Because if you increase this value, it will magically also increase this one because they share a parameter. So if you go over the edge many times, the value of W can increase and increase without any boundary. So one of these things is the off policy, right? It's obvious why temporal difference, it's obvious why function approximation, because that allows me to tie these two states together. But why off policy? Because if we did this on policy, then after going to this node, we would continue. And at some point, we would realize that this is overestimated. Right? Maybe even after this one transition, we would see that this is very large, more than it should be, and we would decrease it when processing this node, and that could counter the effect of increasing the W. It might not happen on a single step, it might need several steps, but generally, if you assume that at some point it will end, and even if not, then discounting will kick in, then once this starts to be too large, the rest of the episode will make sure that we will get an update which will put it back down again. But if we are using off-policy training, then we can ignore the rest of the episode because of the important sampling ratio, right? We can say, yeah, well, this is how the episode continued in the behavior policy, but with the target policy, this is very unlikely, so you will not consider it very strongly, so the update which you get from that would be very little. So with off-policy training, you are actually allowed to go through this one edge many times without seeing the effect later that this is an overestimated value. So let me show you the specific example. Like that one was just like an idea, right? But it can be made into full MDP. It's called by one of the students of the people who came up with this. So here we have got 6 states. You can see that their value is always 2 times their corresponding parameter plus W8. So the W8 will be the naughty parameter, right, which here is 2 times larger. So this is what will be causing the full increase. So we need the behavior and the target policy. So the behavior policy is like uniform in a sense that when we are here, we just uniformly go to one of these states, and if we are here again, we just uniformly go everywhere, right? So the behavior just says jump in any way you want. But the target policy always follows the black arrows. So the target policy is boring, it will get down there and it will stay there forever. So there is +0 reward here. There is some discounting. And we have some initial values, so let's say that all the weights are 1 except for W7, which will be 10. So the optimum value here is 0 because there are no rewards given, right? So that would not be so unexpected. But if we do the semi-gradient SARSA, or even if you do the dynamic programming update, so in the dynamic programming update, you know exactly what the dynamics of the environment is, right? Even if I have complete access to the environment where no stochasticity is involved, where I can do the update really completely, then during the training, the size of W8 will increase above all the boundaries, right? So on the right side, you see the nice and smooth case where all the stochasticity has been removed, while here, stochasticity of the SARSA is there. But none of that actually converged to the 0 where you would want to go, right? Instead, you would say it's larger and larger and larger and larger and larger, and that's it. So that's kind of bad, right? So these three elements combined all together can make your training even diverge. And this was it, until like 2013, where people came and just said, okay, we'll just ignore it, just prove some bunch of old guys are doing. We will just show that it works anyway, right? And then they trained an agent kind of in the setting, so it will be neural network. We will do off-policy training, and we will use temporal difference for doing the estimates in a way that it actually worked. So I already discussed the Atari game playing on the first motivating lecture, right? So imagine that we are in the situation where we have this, like the actions are a joystick which we have. So it's like there are just analog switches there, so it can be 9 different positions, right? We have got like horizontal and vertical axis, each can have 3 values, to the left, middle, to the right, to the top, middle to the bottom. And there is one button which can be pressed or not, so we will have 18 actions. And on the input, we get a screen of an Atari console. So it's some kind of low-res image, 210 times 180. They are kind of colored, contain the color, but it's not very important. And in these settings, we will try to learn how to actually play the games. And some of them are like more advanced than driving your car with a pole on it. Right? There are. But still, they are not very difficult, and maybe we can find someone and play for a bit just for fun to see how difficult they are. But some of them are challenging, and people enjoyed playing them. So what we will do, we will try to train in such a setting, and we will use the Q-learning algorithm for that. So that's why it's called deep Q networks. But we have seen that there is a good chance that the training might diverge. So some care will need to be taken so that it doesn't happen. So how does the network looks like? Well, we will estimate the QSA as you would expect, right? So we will estimate the action value function, and technically it will look not that we pass the action on the input. Instead, what we will do is we will I will just draw it like this. We'll get the state on the input, then there will be some convolutional magic, and then we will get an output of size A, number of actions, and here the outputs will be QSA for all A's in the action space, right? So we give the model the state, and it gives us the expected performance, the expected return of pressing all possible actions in the given state. So then, when we want to choose a greedy action, we can just do argmax on the vector produced by the network, and that will tell us what is currently the best action to take. The network is like kind of simple convolutional network. So we start with convolutions on the images. There are like 2 layers of that. Then we do a flattening layer, do a fully connected layer. So I have some specific numbers here, but the network is not definitely large from the today's standard. It's like a child's network. But still, it was something, at least for the reinforcement learning area. So the images are scaled to be squares because, well, it's easier to work with them anyway. They are converted to grayscale because the color doesn't really matter much. And what people also have used is something called a frame skipping technique. So the thing is, the simulator uses 60 actions per second, and that's quite a lot of them. So to make things faster, what they do is they run the network only at 15 hertz. So whenever they run it, they keep the action and they just repeat it 4 times for the network. This is mostly just an optimization of not spending too much time generating the actions. And also, they use the same thing on the input, so they only consider every fourth frame in the history, right? So what I mean is that we know that we need like Markovian environments. We need the full history to be in the state, right? We cannot consider also the previous states. Everything needs to be there. But if you have just one image, then you don't know many things. You don't know the velocities of the objects. You don't know anything. So what they did to get like a poor man's history is that they consider the last 4 frames, right? So not just the current one, but also the ones before. And the idea is that if something is moving, then you can see it on this slide. So you can very poorly estimate also the velocities and maybe the accelerations of the object. Still, it's not true that you would really see everything from the given state. So this is definitely partially observable only. But it's good enough so that you can actually make your agent work if you see this sequence. And so these frames, they are only the ones which we keep using the frame skipping. So this is like the last one. Physically, this is the 4th before that one, and so on and so on. But what they did is they just made the simulator to run 4 times faster. So from the outer view, they kind of think that the simulator only generates 15, like 15, or it needs only 15 actions per second. Of course, all these games are being run on simulator because, well, running them on the original hardware seems bad. But that's one of the reasons why they have been chosen, I think, because it was cheap to actually run kind of fast simulator on games which are reasonably challenging. So as I said, the network is fairly straightforward. So we start with a large convolutional filter, a large stride, small number of filters and some nonlinearity, and then we continue with 64 filters. And then we do a flattening layer, right? And we do a fully connected layer into some number of units, and then the output layer. So this is like a very simple AlexNet kind of thing, right? Convolutions with strides, and then flattening and the output there. No batch normalizations or anything. Well, this is 2013, so batch norm was still 2 years in development. But actually, when you do reinforcement learning, then you don't really battle too much with overfitting, in a sense that underfitting is something which becomes a serious challenge as well. Or maybe I said it incorrectly. Even overfitting is an actual challenge, but it's kinda, the situation is kinda weird because you get a very noisy gradient estimate. So when you learn something, there was a good chance that many other actions would work as well. So learning one specific action which we have seen might not really be a good idea. You really have like a full distribution of those. So remembering individual actions too much is not really a good idea. So from this point of view, we are overfitting a lot. But also we are underfitting in the sense that the noise and the gradient is so large that if you do an update, there is a good chance that it really won't lead in the right direction as well. And so all this talking is that regularization techniques, which work by injecting noise, don't tend to work well for reinforcement learning because there is so much noise in the data in the first place that adding the dropout or batch normalizations can be tricky. I'm not saying it's not done. Specifically, batch normalizations with the convolutions are combined, but it is not as straightforward as it was in deep learning. Then they said, okay, we have convolution, we'll always use a batch norm, and then that's it. And here, you need to be careful, because if your training is brittle, then injecting additional noise into training can make it like off the edge, and then it wouldn't train at all, or train very badly. So I don't really know of anybody using dropouts in training for reinforcement learning, but there are papers which use convolutions with batch normalizations if they make their batches large enough or something. But if you just do it automatically, it might fail just because of that. And anyway, if you have a very shallow network, the batch norm wouldn't help you that much anyway, right? The batch norm is great if you have a deep network so that you can optimize it better. But for the shallow network, everything works kind of simple anyway. Well, what we will do is we will train the network by minimizing the mean square error, the mean square value error. They use RMS prop, well, mostly because ADAM was still not there yet, because this is 2013. And so what does the loss look like? Well, this is the estimate of the action value function, right? So it's like QSA, right? We use one-step bootstrapping, so we perform this one step, get an immediate reward, and then we will use our estimate in the next state, and the action which maximizes our action value estimate. So this is the off-policy part, right? We consider not what we would have done in the behavior policy, but what we would do with our current estimates in the next state, and that's it. So one interesting thing is that there is weird bar here on the parameters. So one way how to get rid of the problem of this semi-gradient method is that we didn't like that we used the same set of parameters both as the target and as the current value. So the authors, okay, though they do it later, but I will say it first. So the authors, they use two set of parameters. One is the one being trained, and then the other set of parameters, and they call this a target network. So to prevent this feedback loop, right? Because this off-policy problem happened that when we had this these two states, then increasing this W increased our estimate in the following state. So what they do is they have two set of parameters, and one is being used for the current one, but then when we are using bootstrapping, when we are computing this one plus the reward plus the value estimate in the next state, they use a different set of parameters. So if you increase this W, it will not increase your estimate in the next state, because there is a different set of parameters for that. So this feedback loop of getting larger and larger and larger is broken because we have got two set of parameters. And this also helps with the semi-gradient versus gradient, because again, the problem was that we used the same quantity on two places, and now they just use one. This, of course, means that we also need to somehow update it or change it. And so what they do is, well, after some fixed number of updates, they just copy the current value to the target network. Right? So they track the current parameters by really just each 1,000 steps or so, they just copy the current value. So they train it somehow, like it changes gradually, but then it's fixed for a large period of time to avoid these immediate feedback loops, because now the feedback loop has a history of 1,000 steps. And so it won't be such a problem. And if it would happen just randomly, just one random error would reinforce itself, then now it won't. So that's one thing which was surprising and avoided all these problems which we have described. Then the other thing, what we need to do is that when we are training, like if you imagine one game, then it could easily happen that we will play it for 10 minutes or something, and just the specific situation would be encountered. I don't know. Let's say that we have got like two rooms in the game. Either you are in one or you are in the other. And then, like if you get into one, you will spend some time there. And now, if we just perform training on policy, so whenever we just did it, we would also train on it, then this kind of catastrophic forgetting of neural networks could happen, right? If you perform like thousands of updates in this one specific situation, then the neural network will tend to forget everything which worked for some very different setting. Like, that's what the SGD does, right? If you say, okay, let's minimize this specific clause, then if you tried training, I don't know, MNIST digits from 0 to 9, and then you would train for 1,000 steps only 0 and 1, then the network would tend to forget all the other ones because, well, the gradient updates for 0 and 1 will gradually override all this information, and there is no reason why the network should remember. And that's a problem with on-policy settings, because in on-policy settings you need to do the updates immediately, because if you do them later, then the behavior policy would differ from the target policy because it has evolved since that time. So in the on-policy training, you generally need to use the experience immediately when you generate that. And so that's why the use of policy training, and they explicitly use the experience replay. So what they do is they keep something like 1 million of transitions. So the transition, that's like the similar thing as in SARSA. Like that's the state, action, reward, next state, and done. Right? These are the 5 things which you need to actually evaluate this loss function. Right? You need to know where you started, what action you did, that's S and A. You need the next state, right? That's the state where this has led to. You need to know the reward, and you need to know whether the episode ended or not. And that's all. Like if you have these 5 quantities, you can minimize the loss. And so if you keep a large number of these replays, let's say 1 million, then you can generate them gradually when you gather the data. But during training, you can just sample randomly from this replay buffer and then train such a batch. And this avoids the catastrophic forgetting kind of situation, because you will always be like randomly seeing all the situations which you have encountered in the last million steps. So hopefully you will not forget anything important. Well, if it didn't happen for 1 million timestamps, then probably it's fine to forget it. This, like, it is still kind of limited. Like, I know that 1 million seems large, but they do 50 million updates or something. So still, you try to keep the recent version, because the longer the experience replay would be, the more of policy data would be. Like, still, when you think about the states which you visit, then at the beginning, if your policy is bad, you are probably visiting states which you don't care that much about. You care about states which you get into when you play the game correctly for some time, like for the prefix of the game. So you need to somehow forget this old on-policy distribution, like the state which you visited to the old policy, you need to somehow get rid of it. So this will take some time to do it, but still, if you didn't use 1 million, but 50 million or something, it would make your training worse, because you would always consider also the states which you have seen at the beginning of the training, but these might not be relevant for actually playing well for a long time. And so the third thing which they did is they did a lot of clipping. Yeah, a question.
Is it important to sample randomly from the memory?
So the question is whether it's important to sample randomly from memory. I will take, say, 2 views why it's important, and then we will see whether that answers your question. So one thing why it's important to do it is to avoid this catastrophic forgetting thing. If there are like if the gameplay like alternates between two situations, like a green room and a red room, and you would spend a lot of time in one of those, then if you just used your data sequentially, then you could do a lot of updates, like thousands of updates when you see the player in this room, and this could forget everything which you had from the other. So this is like a general problem of neural networks, that if you train for a very long time with only a subset of labels, then all the other labels will be lost. Right? So this is what I meant when I said that if you train the model on MNIST, like recognizing these digits, and let's say that it has gotten to, I don't know, 98% accuracy. And then for 1K updates, I will just train zeros and ones. Then the accuracy on these 2 to 9 would go, and it would be very bad.
Yes, but if you train your left room more often recently, then the expected number of these samples would be still higher.
Yes, but if you did it in this on-policy settings, then it could happen that when you get to the left room, you will spend 1,000 steps there. Right? It could be the case for both of them. Like, let's say that if you get to the left room, you will be there 1K steps. If you get to the right room, you will be there for 1K steps. And like, there is nothing bad into really just doing on-policy training. So sometimes you would be here, sometimes you would be there. So on average, it would work. So I'm not saying the problem is in the formulation or in the math. The problem is that the neural network will forget everything after you will do 1,000 updates in this room for the other one. Because
yeah, but if the memory is long enough, then it shouldn't matter, right?
yeah, but if we would be, so what I'm describing is if I would do an on-policy training. So whenever I get the experience, I'll do an update on it. So then the memory is not something explicit, then the memory is just what the SGD does, like, because the memory is hidden in the parameters. So to make it longer, you can only decrease the learning rate, because otherwise, in each step, you just override some portion of your parameters with a gradient from the given batch. So that's why I'm talking about number of updates, because each update you do will push you somewhere in the loss function. And so if you go in 1,000 steps in direction just of the red room, you will get to some place in the loss function where your behavior on the blue room can be really tragic. You could counter that by decreasing the learning rate. That's the only thing which I know how you would make your memory larger, because your memory gets overwritten by every update in the SGD. But that has some other problems, because if you make your learning rate smaller, it might converge longer. And there are actually episodes which takes like 5 minutes, so really large number of steps. So that's one thing, and that's still not the, like this tries to show you why using this in the on-policy settings is bad. If there are episodes which are larger than the, I don't know, attention span of the neural network, then they can just break the neural network. And increasing the attention span of the network is not very simple. But if we have the experience replay and in every step sample something randomly, then we are like helping the neural network to increase the attention span, because instead of giving it 1,000 consecutive steps, we give it random steps which the agent has visited in this large memory. So that's why how we do this, let's increase the memory kind of thing. But then we sample from the replay buffer instead of processing the experience one by one when we see them. Yes, we are sampling from the like 1 last million elements of the history or something. So that's what the replay buffer is. The replay buffer, or experience replay, is just last million transitions in the history which we have seen. So maybe we can have a look at the algorithm. Maybe that will make it clearer. So this is the algorithm. So we will do it for some number of times. And so during every episode, what will happen is, well, we are collecting the experience data from this episode. So we have started. So this is like the reset of one episode, and we are acting. So we will act with epsilon greedy approach with respect to the Q function. So the same as before, really just with some small probability do a random action, otherwise do a greedy action. Right, so this is like either random or greedy. Then we do it, so we perform the step, right? We do env step, and we will get the reward and next state. So we'll store it, we will compute the features, and this is the part where we store this transition in the history. So the D is the history of all the steps or transitions which we have seen. So like there is this one agent which is just interacting with the environment. It generates data, and everything gets stored in a buffer. If the new episode starts, nothing really happens. We just start again. We just say okay, and this is the last transition in the episode. And then when we do the training, so this part, that's just the experience gathering, right? We sequentially generate more and more data with the current policy which we have. And then the second part will be the training part. And that is like completely unrelated to the current episode. It always just takes the history of the last n steps, and million is what they use. And so we take random million steps which we have encountered so far, and then we do the update. Right? We can have a look at how the update looks like. Well, we compute the estimated return for each of these transitions. Like either it's the reward if the episode has terminated there, or it's the reward plus gamma times the maximum of the return we can get in the next state. But this part is evaluated using the target parameters. Right? So not the one which we train right now, but the one which we use for doing the evaluation. And once we have it, we just do the gradient descent on the mean square value error, right? We don't need any specific distribution. We just have the distribution of the states generated transitively from how we sample from the replay buffer. So we just minimize the square error between whatever our network says with the current parameters and what is our estimate of the average return. And once upon a time, we copy the current network into the target network.
We perform gradient descent on all of them. So there is no random sampling, right?
Well, there is a random sampling in a sense. Then in each step, we just sample a random batch from these 1 million transitions because it's very many of them. So in the same way how if you have a fixed data set, you always sample just some number of examples to do the update. So from this point of view, we don't physically use all the transitions all the time or every time because that would be very costly.
Yes, that's what I'm talking about. So if it weren't so costly and we always learn from the complete history of capacity of n, then it would be the same, right?
Yes. If we don't care about about performance, we could have used the whole replay buffer in every step. And what we are doing has the same average in a sense that the estimates of the gradients are the same, but just for performance reasons, we don't do it. But it's the same as if you are training on MNIST or ImageNet or something. Like we generally want to minimize the loss on all the data, but we just do it per batch because that's cheaper to compute. So from this point of view, we would like to minimize our error in the whole collected experience so that our temporal difference error would be 0 everywhere. So that's what we want, but we achieve it by sampling just because that's what we can compute quickly.
And okay, I will ask later on.
Yeah, but if you have a question to ask, please do. Like, it's better to talk about it than to, I don't know, me showing you a 6th version of that later, right?
So the question is whether it's usually done in the way that you sample only one batch and then go on, or
Yeah, yeah.
is that enough?
Yeah, usually you only sample one batch and repeat. Of course, there is some balance between like how quickly you generate the experience or how quickly you add to D and how many updates you do. So when I do it like this, then I do one batch for one step performed, then what it means is that one transition is used roughly, I will find the batch size explicitly because I don't remember 32. Okay, so the batch size is 32. So in that case, every transition will get to be used roughly 32 times for updating the network, right? Because in each step we generate one transition and then we take 32 of them from the replay buffer. So this means that on average, each transition will be used that much time. And this is mostly the important factor of how many times you want every sample to be used. If you would like to increase it, you might either increase the batch size or do more batches before you collect the experience. Sometimes you will want to go the other way around, so you will generate more experience before you will do the update, because once we will start using batches of 1,000, then you will need to generate more experience. So here in the Q-learning, they really do it like that because using it 32 times seems kind of reasonable, like tens of times. But we will see some other settings in a very different situations.
How often do you actually update for every step in the environment?
Yes. Yes. So when we do one step in the environment, we will also do one update. We could have generated multiple steps in the environment, for example, but then if we did like 2 transitions before doing one update, then we would use one transition only like 60 number of times during training. So we could do it. We would generate more versatile data set. But the question is, how much versatility do we actually need? So it's like a trade-off between how fresh or new experience we get for the compute power that it will cost us. So like generally using every experience like some number of times, like larger units or small tens seems to work reasonably well. But later we will train with very large batches, so then we will need to generate several steps before we'll do an update. And we'll do that by having multiple computers, each generating experience, so that we don't use a single experience too many times, so that we don't overfit on it too much.
Does it make sense to do learning rate decay?
Yeah, so the question is whether it makes sense to do the learning rate decay. So I think it makes sense, but it's kind of difficult to say the length of the training which you want. But I think it would make sense. I would not go to 0, but I would start with the larger one and then decay it in something smaller, but maybe only 1/10 of the original or something. It will still be the case that the performance of the agent will not go like up nicely, but it will tend to oscillate a lot. And here, the good thing about reinforcement learning is that we have infinite validation sets. We usually can simulate as many epochs as we want, so we can evaluate every model to any precision we like. Like if you are going for the lunar lander, and you've got 2 models, you can evaluate each of them on 1,000,000 episodes, And then you'll have a very good idea of which is better than the other. This is something which we cannot do in the supervised settings, but we can do it here. So we can actually choose the best model out of these random changes really just by doing a lot of evaluations, because in some sense they are free, because they tend to, you have a simulator and you can simulate any random situation, or you usually start in some randomized situation. So from this point of view, we don't usually take the agent from the end of the training. Right? We don't need to. It is perfectly fine to select an agent somewhere in the middle. Normally, like early stopping can be tricky because our development set might be limited. But here we have possibly infinite development set. So we don't care much about our training converging to the agent. We are fine if it visited the agent during the course of the training. So from this point of view, the learning rate decay is not that important, but still decaying kind of makes sense because it should generally oscillate in some larger values when the learning rate is smaller. But learning rates are smaller in reinforcement learning generally because we have a lot of noise, so we don't want a single one batch to make too large effect on the performance. Yep. Yes?
There is like speed notation with the queues.
Mm-hmm.
And is it actually a different function of the queue head than the queue, like in the previous?
Yeah, so the queue head, do you mean the queue? Yeah, in the algorithm slides. So they use slightly different notation that I am using. So they just, when they say queue head, then they just mean the target network. So they wouldn't need to do it, and I also don't do it on these things, because here I say it's the same queue, it just differs by this argument. But they do both, right? They have queue always with theta, and then they have queue head always with theta bar or something. But it's the same queue. We have got like one architecture of the network. You just evaluate it with two different set of parameters. And because of this reset of copying the arguments, then they need to be the same. In the later papers, people have stopped using this queue head, so I'm not using it here, even if they do. So this is directly from the papers. Like, I didn't really have time to rewrite the algorithms from the paper, so I was just copy-pasting them directly, so the notation will differ widely between them, but that's, yeah, I probably cannot convince you that it's an advantage that you know how it was in the paper, but realistically, it's just because I don't have time to do it. So that were two things, and we will add a third one, and that will be reward clipping. The size of the rewards is actually quite large. And the thing is, the mean square error here, it depends on the size of the error, right? If you expect to get 500, and then the real target is 1,000, then the gradient of that will be very large, right? Because the mean square error has unbounded gradients. So they do several, like they use several places where they clip the rewards. First is that in different games, the scales are very different. By the way, the rewards are given to you explicitly, right? So when you have this image, it shows the state, but when you do the transition, you also like get the number. You don't need to read it from the screen or something, you just get it. So in every game, there is a score, right? So the emulator just looks at it, and whenever it changes, you will get the difference as the reward. But in some of the games, the perfect games are 99 millions. In some of the games, the best rewards are minus 15 or something like that. So they differ so much that if they want one set of hyperparameters, they wanted to make the scales similar. So they did something very crude, and all the positives reward were replaced by +1 independently on how large they were in the original environment, right? Or the negative by -1. So this can be drastic, right? This can change the rewards from thousands to just ±1. This is also bad in a sense that if there were rewards of +1,000 and +2,000, After the clipping, they are the same. They just say, this improves my score, you don't know how much. Yeah, but they do it. So that's one thing. The other thing which they do is that when there is a life loss, because the simulator also have some lives, so if you lose your life, then they wanted to use this as an important information. So they say, that's the end of the episode. You have just stopped. Right? Because the thing is, this is not a part of the state, like how many lives you have, so you need to prevent your agent to stop losing lives. Normally, it's fine to lose one life if you then can continue later, but if the lives are not the part of the state, which they are not in some of the environments, because it's just what you can see, then they've decided to go this way, like never try, like it's a never good idea to lose lives. That's not really the case, because in some of the environments, like losing one life can be useful regarding or considering many or considering a large history, but right now they couldn't do it, so they just stop it. And the last thing what they do is that even if you clip the rewards, this mean square error can still be quite large. Like, for example, consider the card poll. In card poll, all the rewards are +1, so they wouldn't be clipped, but your return is +100, is 500 maximum, 250 on average. If you imagine training a if you imagine training a card poll, right, then these value estimates Q are like 250 roughly for the states where you keep the poll upright. But when you consider one episode, then from this state, you will see returns of 0 and 1 until 500. So this gradient would be quite large, even if we have clipped the immediate rewards. So they also clip this gradient, right? So normally for mean square error, we have got these gradients, and they say, okay, 1 is the largest, so it will actually look like this, right? So it's just the Huber loss, if you have seen it. If not, you can just really think about it as a gradient clipping of the gradient which comes out of the loss. If it's larger than 1, I will clip it to 1. Yep. So now let's have a look at how this went. Yeah, question? So the question is, if we didn't scale the rewards, what would need to happen, or how we could adapt? Well, you would need to change your learning rate. Because the learning rate can scale, because all these things will scale the gradient. So you can counteract by scaling the learning rate down significantly enough to deal with it. One thing is that things like RMSprop or ADAM should help you. Because when you look at the loss, then if the loss is too large, like if you imagine that your rewards would be 2 times as large, then this is something what the ADAM or RMSprop should normalize for you, right? Because if the values are some constant times larger, then the gradients are just constant time larger, and this should go away by normalizing the gradients. So in some sense, RMSprop should have helped them, but I still think that you would need to fiddle with the learning rate more to make sure that it works. And for some of the environments, I'm not really sure if it could work in a sense, whether they could be able to train it. Especially the clipping, the second one would probably still need to be kept. But if you like normalize the rewards instead of doing this manual clipping, if you change the reward so that if you are given a reward, it would be of 1, or in the absolute value, the expected value of it would be 1, then you would probably be in a very similar situation. So I guess that could also work, and we will see many improvements on this front. So we will see approaches which will do this, which will normalize the rewards in some sense, and that will allow us to train across environments. But for the time being, this is what they did, and this is what it works, and it has taken people 4 years or something, or even 5, to do something nice and systematic about it. And we will see how to do it nicely nowadays. So of course, nowadays you wouldn't do this clipping because you lose information, and that's the problematic part. Like plus 500 and plus 400 are the same from its point of view, which is suboptimal. So, these are the games where they evaluated on, and they had some best state-of-the-art, which are the gray kind of things, and the blue one, which are their performances, and also there is this human level, right? So the human level is set somehow weirdly, because they have this human normalized score, and so 100 means the same as our players. Like, so what they did is they have taken the human players, let them train each game, like for each game they've chosen some set of players, each has trained it for some time, and then they played. They played for 5 minutes initially, and then for 30 minutes in some later experiments, and these are like human normalized scores. Now here in this table they say that 75% of the human score, that's like a human level, right, instead of putting it to 100, which is where we would expect it to be. And also they evaluate, like in this Atari settings, there are 57 different games, and they evaluate only 49 of them here, and it's such a coincidence that the games which they missed are the ones the machines are terrible at. Right, so in fact, there is like 8 of them more, which are mostly lower than upper. So from this point of view, it is like an exaggerating lot, kind of. But that's what they say. But anyway, still, the best what people could do were the gray bars, and now they came up with the blue ones, which was definitely very nice. So I don't know, maybe this one is more interesting. So here we have a Pong game, like that's, you control this bright green thing, and you can either go up, down, or do nothing. So here what you can see are the action value estimates in this situation. So when the ball is going close to you, then right now all 3 actions have a good estimate, so it seems that something positive will happen. But if you wouldn't move and the ball would move a bit, then you would see that, well, right now only going up is a good idea, right? If I go down, I'm expecting -1 because that's the -1 for losing, and we have the discounting, so it could be even larger than -1, right? Because we will get -1 immediately and maybe something later. But it seems that the rewards are given so sparsely that the +1 to -1 to +1 range seems like a reasonable thing. So this kind of works fine. There are some situations, for example, here where the ball has gone through the enemy, that we get a good outcome independently of actions. That sometimes happen. Sometimes your actions won't influence anything at all because it has already been decided. So you will get something interesting later. So this is what the neural network actually computes, right? But here we are showing 3, even if there are 18 actions, but generally they are like of these 3 groups. So let's have a look at how they trained it. So these use a mini batch of 32. The replay buffer size is 1 million. So the target network update frequency. So every 10,000 steps, they copy the target network, the current network into the target network. This, if you are training, this is a tricky hyperparameter because this means that you will improve your estimates only each 10,000 steps. But you'll probably need to do this many times, right? Because you will, without this, like when you copy the values to the target network, that from then on you will compute your estimates using the policy which you have right now. And then you will be updating the policy, but the target value is still being used to estimate what would happen, like what will happen in the rest of the episode. So this somehow evaluates like this specific policy, and in some sense, like this policy is being kept because that's what tells you what's good or not. So you will need to do many of these steps. So if you will start training your network and use this hyperparameter and set it to 1,000, then expect to do millions of updates before something interesting will happen, right? So when you do this manually, you definitely want this to be small to see something is happening, but if you make it too small, it will diverge, so it's kind of a trade-off. So the discount factor is 0.99, and now this is tricky, because we need the discount factor during training, but we don't evaluate using such a discount factor. The evaluation is performed by you playing the games for 5 minutes or 30 minutes, depending on the settings. And there no discounting is happening. You will really just be summing the rewards in this very large but fixed window. But during training, if you didn't have any discount factor, then the training would work very badly. The reason is that if you look at the loss, you use the discount factor here. So if there is some error in the estimate, this gamma makes the error smaller. So it's a way of like ignoring some of the errors which you have, because you will just say, okay, so let's make it smaller, right? This also means that your action value estimates, like the numbers which you have, won't be very large. Right? They will be kept in some given range, because if you imagine that every reward is 1, then the action value function can be unbounded if you have many possible steps. But if you use gamma of 0.99, your Q will be limited to 100, right? Because, well, 1% of this will be 1, so you cannot get, or shouldn't, or the real function will not get above that. So the discount factor which we have here is there for training, to reduce the variance of our estimate. But we don't want it during evaluation. So this is bad, because the discount factor actually changes the environment. Like, the thing is, if we actually wanted to do this, then we would consider our behavior only on the first roughly 100 steps or so, right? Because if we really consider the discounted performance, it would be so small after hundreds of steps that we wouldn't care. But there will be episodes of 30 minutes of playing a single game, and we do evaluate it by summing. So this is a very big discrepancy between the discount factor, like what we say what it is, and what we actually do with it. And we are actually having a different training objective to the testing objective, and we will see how that will improve in future. But right now it's there just for the method to train. So they train for 50 million updates. That takes several days of training, definitely. The learning rate is said to be a very small number, right? It's 2.5 times 10 to minus 4. And they by the way, they use RMS prop with both momentas, both the first and the second, so this is nearly ADEM, really, right? Because the only difference between RMS prop with 2 momentas and ADEM is just the bias correction, which is there for just first few thousand of steps, which we don't care about given that we are doing 50 million updates anyway. What they do is they do a lot of exploration at the beginning. So their initial epsilon is 1. They start by doing just random actions. And they decrease it to 10% in the first million steps, right? So they generate 1 million random transitions where the epsilon goes from very large to small, so that they really just try a lot of things. At the beginning, the computer is really just randomly putting the joysticks on all the directions and hope to see something interesting. So this gradually goes down, and then after this 1 million transition, it will be kept as 10% for the remaining of the training. And at the beginning, they generate at least 50,000 transitions before they started training, right? Because otherwise, they would repeat a lot of transitions, and that would get them probably to some local minimum. So, but even if this is tricky, it still worked, and people were surprised. The paper, which was originally on arXiv only, has gotten to Nature, and Google has bought DeepMind and things like that. So that means a lot of people started looking into the same thing, and many papers were released about like various improvements of deep Q networks in the next years, right? You know, because somebody was actually made or was able to make it work, even if the theoretical results said it will diverge, don't try it. But once somebody has done it, there was no point in, a lot of people were actually able to succeed as well. So we will now talk about various improvements. There were really many. So what we will do is we will describe a paper which is called Rainbow. Like Rainbow is like the deep QN on steroids. So how does it work is that 4 years later, in 2017, the people also from DeepMind considered all possible or the many improvements which the community has proposed in the last 4 years. And they took 6 of them and combined them all together. So they were such improvements which could be combined, take them together, and they showed that it actually works nicely. So this gray line here, that's the original deep Q network. Here you can see a median human normalized score, right? So it's like a human normalized means 100% is people, and it's a median. So that's like if you look at the games and at the middle one, how well you are doing, then what you can see. So there are the 6 individual colors are the 6 improvements which we will all describe. And then when you combine all of them together, you get this rainbow curve, right? And generally, like the idea or their point was that all these improvements really like support each other. So by incorporating all of them, the performance actually increases above the performance of every individual one. So we will not go through all of them, but we will go through some of them, and then we'll leave the remaining ones for the next lecture. But we will start small. We talked about the maximization bias in the tabular settings. And the same problem is also happening here. The fact that we use the same estimate for choosing the action and then evaluating it means that we are too optimistic. So that's the same problem as we have seen. So previously we have solved it by considering 2 action value functions and training each of them independently. And then when we choose the action, we choose the best action according to one of the action value functions, and then evaluate it using the second. So we could do something like that as well, but they came up with a different solution to the same problem. And what they say we already have 2 action value functions, the current network, and then the target one, which we use for evaluation. So why generating next one? Let's just use them. Right? So instead of choosing the target policy or the target parameters, both for choosing the action and then estimating its value. We will choose the action with the current behavior, right? So whatever the current policy thinks is the best. And only the final evaluation will happen with the target network. So still, we have broken the cycle, because what we cared about was this evaluation. Like, this was the problematic part where we didn't want to use the current parameters, but we don't care much about generating the action with the current policy. But if there is some maximization bias, if this target policy thinks that some action is better than its real value, then we won't be able to iterate on it or something, because we are choosing the action with the current policy, with the current set of parameters. So the maximization thing would happen only if both of these think that some action is better than it should be, right? So it is actually enough to solve or deal with the maximization bias problem. So here, what they do is they generate very manual data. So they really generate like value estimates with some noise in them. The errors are independent normal random variables, so very simple settings where you just see random noise for every state independently. And they look at what is the difference between it's very small, isn't it? So what's the difference between using just one action value function, so just using this minus the true value, or using this part minus the true value? And the red ones, the increasing ones, are the original one. And here in this axis, we have more and more actions. Like, if you have more and more actions, there is a chance that this one action will get overestimated more and more. While these invisible blue ones are the ones where you just include, sorry, I didn't do it enough, where you will just use this part to do it. So it seems it's kind of enough because the blue bars don't seem to increase, right? And the good thing is that this is cheap. Like, this cost us nothing. Because we already had a two set of parameters, so it's just a different way of computing the estimate. So the good thing is that it is kind of trivial to implement. They had more visualizations to really show the problem as well. So what they did is they had some data points, and they tried to fit the action value functions on those. And what they did is they considered data with two states missing, right? So the idea is, okay, we have got some approximations. These approximations don't see all the data, so only just some of them. And so they fitted the Q value estimates for the data sets where every 2 points were missing. So the violet one, that's the true one, right? And the green one, that's the one with which the algorithm fitted. And then what they looked at, what is this maximum over all those actions are. So over all these situations where you considered different points missing. And generally, the maximas tend to be quite bad, even if the average or like the average error is not bad, but if you look at the largest one, the results are really bad. So with the double Q estimate, the one which they use, the average error is being much more nicely handled or limited, while in the usual maximization bias thing, just one bad estimate for one action will really blow the error through the roof. So what they also show this in practice. So when you have the environment with various games, then what they do is they show the performance of the agent, like they train. So for example, these red lines, what they do is they show what the DQ and itself thinks how good it is, right? So the maximization biased things, the deep QN. So it is fairly optimistic, right, how it's going. Its real value is this bottom line, right? So it is overly optimistic of what it should do. This real value is at the end of the training, right? So that's why it's horizontal. While if you use the double deep QN, then this is the estimate and the true value, right? So generally, you can see that it is much more accurate than the red one. Not perfect, but still better. So just this simple trick was able to give them quite large improvement. So what does these numbers mean actually, right? So right now we are showing the original evaluation from the DQN paper. So they had 49 games, and for each game they considered at most 5 minutes of gameplay. So if you could play for 10 minutes, it didn't matter, just 5 minutes were taken. Of course, if your game ended in 30 seconds, then, well, that was it. And they also wanted the performance to be like stochastic. But the thing is, the simulator is deterministic, the emulator which is running these games. So the problematic part is that the algorithm could have learned one perfect episode, and it would just do it all the time. And the thing is, the states were not randomized in these console games, right? So it could, the algorithms could work not by adapting or by learning how to behave at different states, but just finding one specific path through the space. So they did it very poorly at the beginning, and they used something called no-op starts. And that means that they considered 30 different scenarios where at the beginning, from I don't know, 1 to 30 steps, they wouldn't do anything. Right? So they would force the algorithm not to play anything at all for some fixed small number of steps. So they have generated 30 different deterministic settings and at least evaluated on those. So that's what we are seeing here. And the median and the mean are kind of obvious, right? The means are much larger than the medians because there are some games where the scores are very large. And the computers can do it, right? So in games like pinball, the machines can generate 10 times or 100 times more than a human, and that will skew this mean to really a very large number. So mostly people care about medians, where the median just tells you how good you are on the middle of your games, right? You will just look at what your games like you just order how good you are. The median just tells you how good this is. So you know that all the better games are better than that, or the worse games are worse than that, but it's just 1 point. So the good thing is that it is not influenced by the outliers, but the bad thing is that you don't see how good you are doing apart from this middle performance. Yep. So from then on, people realize that this 5 minutes, that's definitely too little because many episodes can go on longer. So people started using 30-minute evaluations, and that's what people are doing until now, so that hasn't increased. And also, instead of using these no-op starts, in the later evaluations, we will be using something called human starts. So the thing is, when they had the players play the games for the evaluation, they also recorded what they did. And so for each game, they had several initial plays of the individual new humans, and so these are the ones which are now being used for evaluation. So during the evaluation, some prior human plays for a fixed time, and then the machine continues. But the idea is that these are the states which the machines might not have visited at all, right? Because it doesn't know a priori what the people actually did. So that's what people have started using from that on. As far as I know, these data don't really lie anywhere around. So it is probably possible to get them by writing to the authors, but none of the papers say download the data here. But it kind of makes sense to keep them private because you don't want to use them during training. But I don't know what kind of policy they had to actually obtain these data from the authors of the study. By the way, I've probably gone through the break. Do you want a break? Yep. So let's have a break. Sorry for me not realizing it. So I hope you are ready, enthusiastic about what improvements we can do to make our DeepQ network to work better. So we have started doing better evaluation. So from now on forward, we will use this 30 minutes human starts kind of setting. So with the double DeepQ network, when they use the same hyperparameter settings than before, then they actually improve the results. And here you can see that in this 30 minutes human start settings, the DeepQ network are much worse than how it looked before because their performance has gone down considerably. So in some sense, they were probably overfitted on these 30 possible settings, which like with the no-op start, there is a good chance that you will see all of these episodes during training, probably because they differ very little. So just using double DeepQN improves the performances considerably, and here are also various hyperparameter changes. I don't really have a list of what they did exactly, but the idea is that they want to show the changes in the algorithm and then the change of the hyperparameters, which allow them to improve even more. So that's the double DeepQ network. That's for free, right? You want to do it mostly all the time. So the other improvement, which we will talk about, is kind of interesting. It's called priorized replay. And when we train, we use this TD error, like the difference between our one-step estimate and our current approximation. So that's the thing which we compute the mean square error of. Or square of probably would be better. But the thing is, if on one transition the TD error is very small, then we will learn very little. Because really the gradient of the update depends on the TD error. So if we can behave well in most of the cases, and just in some of them we are off, then we will need to be lucky and hit these bad cases when we sample them randomly from the replay buffer. So here the authors say, okay, so let's instead consider or concentrate more on the transitions where the error is large. If the TD error is large, our gradient will be large and we will learn actually something. So what they propose is to sample the transitions not uniformly from the replay buffer, but according to this probability P, which is proportional to the TD error, right? So we have got the absolute TD error, and here we have some hyperparameter W. So that's there so that we can control how much we actually follow this TD error. Yeah, so this is omega, what I said. I probably said W, but it should be omega. Thanks. Do you want a Raiche? Yeah, that's the way how you can do. You can get refreshed by asking questions. I'm by no means paid by the companies selling tomatoes. So the omega. The thing is, if this omega is 0, then we get back to our previous behavior because this will be uniform. Everything to 0 is the same. So on the other hand, if if omega is 1, then we really use the full TD error, and in between we do something in the middle. right? So the strength of the omega allows you to go between a uniform sampling, so ignoring the TD errors, and taking the TD errors into account a lot. Yeah, so I just said it. So at the beginning, we want every transition to be used at least once. So what happens is that when you collect a transition, you insert it to the replay buffer. What they do is they use the current maximum probability because they keep it around. So they give it like once a very large quantity so that it will be used at least once because, well, it's a new data. Like, even if our error is not very large, it increases the variety or the different inputs which our network could get. So they want to do it at least once, and then when they reinsert it for the second time, they will do it with the correct TD probability. So from then on, they will only sample it if the probability is large enough. So of course, when we estimate with double deep Q-learning, we use the double deep Q-learning formula for doing the estimate. That's just how to combine the two improvements which we have just seen together. Nothing difficult there. However, when we sample the things from the replay buffer, according to these distributions, we no longer sample it from the distribution of actions, how we visited them in the episodes, right? But we wanted that. We wanted generally to use this state distribution, which concentrates more on the states which we actually visit in our episodes. So if we just use these TD probabilities or probabilities proportional to the TD errors, then we could forget how we behave in like the usual boring states. So we need to deal with that. By the way, this thing, that's what I mean when I say proportional to, right? So what this means that if I want to get all the probabilities, I would take all these numbers and normalize them, right? So I would sum over all other probabilities or other these numbers which I have. So this thing on the right, that's not a distribution per se. These are just numbers, right? But you can make them into a distribution using this sign by considering all of the transitions in the replay buffer and normalizing by them. But when you do the sampling, you can do it effectively. So we will see. So I just wanted to make sure that we know what this means. So back to the problem that the probabilities proportional to the TD errors could concentrate just only some small subset of states, for example, or something. So in order to deal with the problem, we will use importance sampling, right? Because what we wanted to do is we wanted to sample the states uniformly. But for some technical reasons, we preferred to sample them according to the TD errors. But we want our action value estimate, the Q thing, to consider the states visited in the episodes, not to consider the distribution of the states generated by the TD errors. But we already know how to deal with that. If we are generating samples with one distribution and we want to estimate the expectation with another distribution, we can just use importance sampling. Right? So that's what we will do here. We wanted our target probability, in some sense, we wanted to sample the transitions with probability 1 over n, where n is the size of the replay buffer. Instead, we have selected according to the probability pt. So whenever we do a gradient update, we will multiply the gradient with this quantity. Right? So what we are computing, the action value function, considers the states according to the state distribution, even if we are selecting them according to the TD errors, because we think that will make the training of our model statistically efficient. And so if you remember, with this important sampling, it can happen that this number could be very large, like this could be 1,000 easily. But we want to avoid that, because if this is large and we multiply gradients by it, we could have a gradient explosion. So what the authors do is they normalize these row vectors, these important sampling ratios, so that the largest one is 1, actually, like 1.0 in the data set, right? You can look at it as if they would be scaling down the learning rate automatically, so that the largest of these vectors, when multiplied by the learning rate, would be 1. So if there are large jumps to be taken, they make sure that we take only small jumps. But whenever you'll be able to get rid of the quantities which are, or if you could get rid of the quantities which are very large, then you are free to actually increase your learning rate. And they also use beta here so that they don't take it like too, the numbers are not too extreme, right? Because these PT numbers can be kind of smallish. Like if you make a very small TD error, then this could be very small, so this could be very large. So one way what they do is they use beta of, I think, 0.5, which will make the very large extremes to get closer to 0. Yep.
If we divide it by the maximum PI, or the PT can like still be super tiny, like 0.001, we can still get like some exploding.
Like here or here?
Here, the PT here can still be super tiny, even though if we, like if the max PT.
Yeah. Yeah, but this is not max PT, this is max row I. Right, so when we consider all these row vectors, right, some of them will be large, some of them will be small, but we divide it by the largest of them. So this will make sure that all the row T's are there. So exactly as you said, if we did it on PT, it wouldn't work, but we did it on the row vectors. And that means we probably somehow consider minimum or something right here, because it's on the other part of the denominator or fraction. So how does the algorithm changes? Well, we still generate the data in the same way. But when we add data to the replay buffer, we add it with the priority, which is currently the maximum one, right? Because whenever we add something to the replay buffer, we give it a priority, and the priority will be kept until that transition is sampled from the replay buffer, and only then, when it's re-added again, we will recompute it. We, in theory, could recompute it all the time, of course, but it would be very costly. So we just do it one time. We just compute the real TD error whenever we are putting it in the replay buffer. It's not really probability at this point. We call it priority because that's what the structure we will have. We will have a structure where each value will have some kind of priority, and you can imagine a distribution by normalizing all the priorities which are there, but the sampling algorithm will take care of that. And so for training, we will sample the transitions according to the priorities instead of uniformly, right? We will compute the important sampling weights, and we will do the division here. Then we will do the usual stuff. So we will compute the TD error, and with the TD error, we will update the transition priority, right? So for this one transition, we have just computed its estimate because we needed it for training, so we can also use this as the new priority when we re-insert it back to the replay buffer. And then we do the update, and when we do the update, we multiply the gradient here by the important sampling weights. Yeah. Here you can see that they have explicitly the mean square error computed in a sense that if you'd implement it, you would probably just say this is really mean square error with a sample weight of omega. But here they write it in a sense that they have the TD error there explicitly, which means that they have already, instead of saying, okay, this is just like Rj plus gamma j times the Q target, blah, blah, blah. So that's the estimate of the return minus the current Q value estimate squared. Then they already say, okay, we have computed the derivative of that. This has gone away. This is the TD error, so that's the quantity which we have added there. And only the derivative of the approximation, of our approximation is used. I don't know whether I'm just talking too slowly about that or too quickly about that. So feel free to stop me if you don't know what's happening, because it makes little sense for you just to be sitting here and watching me dance. We have really much more time than we had in previous years, so I think it makes sense to. So, but that I don't know, right? Because now you are tired. So either you are tired, or you don't know, or you have resigned already. So if I am too quick, please break me. I will be happy to write everything more detailed. Nope. So either you don't need it, or you are too resigned already. So this, I will not show you the evaluation immediately because we will describe one more improvement, and then we will show the evaluation, and then we will go home. So we will keep the priority replay, and we will do one more thing. For some reason, I don't really understand the name that much. It's called dual-link networks. It seems like we'll be fighting with each other or something. But the idea is, okay, when we compute this QSA, so how good our policy will do in some given state and action, then the thing is, sometimes, independently on what we do, it's either good or bad. If we have thrown a bowling ball already and it's rolling, it doesn't matter whether we are jumping or lying or sipping Coke or anything, right? The direction in which you have thrown the ball is the thing which is important. So no matter what you do, the outcome is already predetermined. But when you just estimate the action value function SA, then you need to learn this, that for all the actions, it's going to be the same, and it's harder, right? Because if you have got 18 actions, then you independently for each action need to learn that you are out of control now because it has already been predetermined. So the idea of these authors were, okay, let's train two estimates. Let's train one estimate just for a given state, so you can think about it as a value function independently on the actions. And then let's just learn an advantage. So for every action, whether it's better or worse than the average. And the idea is, okay, so if the network gets, or if your return only depends on the state, it will be much easier for the network to learn it because it has a single place which can be used automatically for all possible actions. And the different actions will only be there to differentiate the result. So for these cases where the state itself determines the return, this could be more efficient. Problem is that if you just say QSA is just VS plus a SA advantage, then there is no guarantee that the neural network will actually use this V as a value estimate. It could say, yeah, this will be all zero all the time, I don't care about it. And I will just store everything in the advantages. So in order to motivate the model to do it, right? What the authors propose to do is that when they compute the advantages, we will always center them, right? So when we take the advantages, we will first subtract the mean from them, and then use that and edit it to the value. So this means that the expected advantage is always 0. That's how we have computed this, right? So this means that the network needs to use the V to really be the value estimate independently on the action. Now, in the slides from the previous year, I said that this was a value function, but that's not really the case. It's very similar to a value function, and they even say it in the paper, but they are also not right. And the difference is that the value function would consider the actions according to the policy, right? How well you do if you take the actions which your agents want to do. But what they do is they just consider the actions uniformly, right? Because when they do this centering, they do it for uniformly choosing the actions. Now, it's a very minor mistake or difference, but we will be actually using these advantages and the value functions later, but this is not really it, because they don't have a distribution over the actions. They don't know it, we don't have a policy, we can do it. So, but this is very close anyway, so I will behave as if it is a value function, but know that it's actually not. So instead of doing this, right, of having the convolutional beginning and then a large hidden layer and then the vector with size of A, we will use the shared convolutional backbone, and then we'll have two hidden layers, one which we'll use to generate the value, and the other to generate the advantages that will be normalized, and then we will sum them, and we will get the vector on the output. No other changes to the training or something, right? It's just change the architecture of the model so that it's more that we prefer to model the returns independent on actions in one place, right? Because the network cannot do anything else. If some outcome depends only on the state and not on the action, it needs to be learned by the value function. Because increasing all the advantages will do nothing, as they are always centered. So the good thing is that in various evaluations work, I will maybe get rid of the boring evaluation. Instead, let's have a look at the gaming evaluation. So this is a very simple car racing game where you go and then you are always faster than your opponents, but the important thing is to avoid them when they get closer, and you also need to steer to the left or to the right. So when there are really no other cars around, it doesn't matter too much like locally you don't have to avoid anything, so it will be the value function which will just look at the far future, right? You know that generally you want to go to the right, but you don't need to concentrate locally. It's just mostly the state in which we are in the sense that it doesn't really matter which action we are going or doing in the local neighborhood. On the other hand, the advantage says, okay, I don't see anything interesting here, because the doing different actions right now makes very little difference. On the other hand, if there are some cars around you, then even the advantage function kicks in, because now it's important to really steer away from those, not to get hit by them. So it's not guaranteed that this change, the dueling architecture, will help. But if the environment actually does this, if there are many cases where just the state influences the return, it will be statistically easier or statistically more efficient for the network to learn it, because it has on this only one value which is actually being used to model this. Okay, seemed like you want to ask, but
it helps because the variance is like lower, because the variance of the advantage is lower because of the state.
so yeah, the question is whether it helps because the variance of the advantages is lower. I would say differently, in a sense that if so maybe I will go through the boring example. Imagine that we have a corridor environment. And we just start, we need to go to the right and then to finish the environment. And so there are like some actions like left, right, up, down, and no action. And what we will do is we will add more actions, and each of these new actions will do nothing. And the important thing is that because they don't do anything, we don't care about them. But if you think about how you are evaluating a state, you are evaluating a state by consider the maximum over all possible actions which you can do in the state. So our evaluation needs to know that the actions don't do anything interesting, but we don't know it per se. We need to use them and like simulate all of them. And if we train independently on them, then you can imagine that we have got these many QSAs, and then when we learn about this one action that it doesn't do anything, it will only influence that one action. So to learn that like 20 actions doesn't do anything, we need 20 data points, each saying this action doesn't do anything. When we have this value function, then like this happens like automatically in a sense that even just like when nothing happens, we generally say nothing mostly happens in that state. So we are like statistically more efficient in a sense that we don't need that much data to model the real behavior. But if the actual behavior would always depend on the action, then using the dual link network wouldn't help us because... Great. So now let's have a look at the results. So here we will see not just the dual link network, but also the one the network with priority replay. So first, from now on, people started to evaluate really on all the 57 games, including the difficult ones. I didn't really found it's not like the 8 most difficult, but generally they were difficult, and I couldn't find any reason anywhere why they were not selected. Maybe it was just an omission, maybe that they didn't get enough players, or maybe it was. Anyway, from now on, it will always be all 57 games. So what we can see here, this is the 30 no ops, so this is the evaluation where we do 1 to 30 no operations. At the beginning, these are human starts. So the Nature DQN, that's the official DQN from the Nature journal. So then they say that's the one reported in the paper. For some reason, they don't show such a large decrease here. Like if you remember in the double deep Q learning, they showed 80 to 40. But the problem is that there are 2 DQNs, right? The one reported in the 2013 in the archive paper, and then the one which they reported in Nature, and that was retrained slightly. So that's why they are careful and say Nature DQN. I'm sorry it's such a mess, but that's how it is. Yeah, they definitely didn't do in the original paper, so I don't know. Maybe they all even retrained it. In many cases, people retrained the agents of others because people didn't release it. So I don't really remember correctly right now. But the idea is, I think that they retrained it. I even tried to find it in the paper, and they don't say anything explicit. They just say the Nature DQN architecture. So somebody need to train it, and my guess is that it was the authors, but I don't really know. So I'm fabulating a bit right now. But I think they even show results of that. So my best guess is that they just retrained on it because it was known how to do it explicitly. So. That's a possibility as well. Even I think the evaluation in the human start settings needs to be done in this way, because if you want to do the evaluation, they didn't give you the trained agent in the original paper, so you probably need to train it yourself anyway. Thanks. So what does this single means? well, that's like the usual architecture. So not dueling, not V and A, but a single. So that's like their set of hyperparameters which they have. So they also have single clip, where in this clip they clip the gradient norm to at most 10. So they definitely do the clipping to 1 here, and now I'm embarrassed to say I don't know if this didn't do any clipping or if this did the clipping of 1. That's the 2 possibilities. I'm sorry. I will learn to the future. But generally, it seems that like fiddling with the clipping helped, but I don't know if increasing it or decreasing it worked. Sorry. But the interesting thing is that if you then add the dueling architecture, well, it helps, not dramatically, but it does. When we include the prioritized replay, right, then the thing is, the differences in the medians are not that large, but the differences in means are kind of large, right? So it doesn't help us with our like average behavior, but the prioritized replay helps us a lot to improve the performance when we are doing really, really great. So if we can, so one thing is that it doesn't increase exploration, but it increases our chance of exploitation. So when we see some good episode, we can make it like we can follow it without making an error, because well that's what we did. Like we wanted to minimize the error of our prediction, but it doesn't help us with the exploration much, which is or at least that's how I interpret that this number does not really increase. Yep. So thank you very much. We'll keep 3 more improvements to the next lecture, and then some more stuff, some new stuff. So at on the next lecture, we'll start doing something which we didn't on the previous lecture. Woohoo! So be prepared to a chaos which will happen. Thank you very much for your attention. Come to the consultation if you want. Ask on Piazza. All the questions which gathered during Sunday will be answered today at least. And enjoy your week. See you.